Our next speaker will be John Morgan. John is currently director of the Simon Center for Geometry and Physics and also professor of mathematics at Stony Brook University. He spent most of his career at Columbia University, where he was twice department chair. He played a very important role in the verification of Perelman's work in the Poincaré conjecture. He and Gang Tian worked very hard to produce a book which was critically refereed and was part of the verification work. So, John?
Thank you very much, Jim. Well, it's a great honor and pleasure to be here. I'm not sure it's such a pleasure to follow Sir Michael, who's given us this fantastic tour d'horizon, but nevertheless, here I am. I think of my talk, if Michael's was the prologue, mine is the post-prologue. This is still warming up for the main act, and I guess my job is to tell you what topologists were doing for that 100 years, why they didn't solve the Poincaré conjecture, how they tried to attack it, and what they managed to do instead, which in fact they did a lot, they just didn't manage to solve the problem that Poincaré had posed. See if I can work this. So the story, as far as I'm concerned, starts with Poincaré's paper entitled Sur l'analyse situs, which was the name he used for what we now call topology. And I think the purpose of the paper, as he says explicitly, is to put topology on a footing as an independent subject of mathematics. It had been inextricably linked to geometry in the work of Gauss and Riemann, as Sir Michael alluded. And Poincaré wanted to set it up as an independent subject. He thought it had a validity in its own right, and it was an important subject to study. He introduced, in this paper and the complements that followed it, he introduced many of the notions that are fundamental to the subject. Poincaré duality. Michael talked about the homology of a manifold, which measures the number of holes. Poincaré duality says, amazingly enough, the number of holes in one dimension are related to the number of holes in the dual or complementary dimension. That's Poincaré duality. He introduced what he called the torsion coefficients, which are the part of the homology that are of finite order, the torsion in these homology groups. And he asked, his first attempt at the Poincaré conjecture was, if a manifold has the homology, that is, the Betti numbers are the same as those of the sphere, and it has no torsion in homology, then is it homeomorphic to the sphere? And that was his first attempt at the Poincaré conjecture, and he stated it in all dimensions n, motivated by what was true for in dimension 2. The 2-sphere is the only surface with that trivial homology. The paper that really concerns us today is the fifth and last complement to analysis situs, where Poincaré undertook a much more serious and profound study of three-dimensional manifolds. So he was concentrating now just in dimension 3, and one of the main points of the article was to give a counterexample to his original question about the homology characterizing the sphere. So one of the main points of this long article was to construct a manifold, a three-dimensional manifold, with the homology of the 3-sphere, but which is not homeomorphic to the 3-sphere. And as Michael said, the way he could distinguish this manifold from the 3-sphere was the fundamental group. And later in this talk, I will actually show you Poincaré's description of this manifold and how he did the calculations. Now, how did he study three-dimensional manifolds? Well, he used a technique that we still use today that's been very, very successful. It goes under the name of Morse theory or a Morse function. So imagine your manifold of any dimension sitting in a higher dimensional space and start slicing it by codimension 1 linear or affine subspaces, and you'll present this n-dimensional manifold as a family of n-1 dimensional manifolds that vary and undergo certain singularities. If you choose your slicing, the direction of your slicing generically, those singularities will be quite simple. And if I have some chalk, I'll just draw you a picture of a surface, how you might slice it. And this is a standard way to produce a Morse function. Maybe many of you have seen, well, let's take a very simple example. If we take the two-sphere and we simply slice it by horizontal planes, we'll get, well, nothing until this value where we get a point. That's a singular space. Then we get a family of increasing circles, decreasing circles, and then the final point, and then nothing. So we present the two-sphere as an expanding and then contracting family of circles with singularities here and here. Take a slightly more complicated surface, the torus. Again, let's slice it by horizontal planes vertically. This time we'll have 4 singularities. The initial one, the final one, and these 2 intermediate singularities, which reflect the fact that the sum of all the Betti numbers of this manifold is 4. There's a Betti number H0, rank 1. There's a Betti number H1 of rank 2, and a Betti number for the second homology, and that gives us a total of 4, whereas for the sphere we only have the homology in degree 0 and 2, and the 2 critical points. There's a very close relationship between the critical points of these slicings and the homology, and a whole calculus of how to compute the homology from these slicings. Well, this is what Poincaré did for the 3-manifold, but he wasn't interested just in calculating the homology. He was interested in understanding a presentation in terms of simpler objects of the entire 3-manifold, and the picture that he produced goes under the name of a Heegard decomposition. It had been introduced by Heegard earlier. So if you take an appropriate slicing of the manifold and you look at sort of halfway through the process, you will find that what's below your slice is what's called a solid handle body. I've tried to indicate one of genus 2 there. So its surface is a standard surface. The picture I have here is of genus 2, but that's the level, that's this intermediate slice. But what's below the intermediate slice is the interior of that surface standardly embedded in 3 space. So that's a solid handle body. The one I pictured is of genus 2. There's clearly one of any genus you want. So that's what's below your critical level. What's above your critical level is the same. It's homeomorphic. It's another solid handle body. So you have 2 very concrete, compact 3-dimensional spaces with boundary, and your manifold is made by gluing those 2 together. And of course, the difficulty, the interest, all the complexity comes in how you glue those spaces together. So this is how Poincaré wanted to study 3 manifolds. The whole problem reduces to questions of how you glue one solid handle body to another by a homeomorphism of the boundary. And this is what Heegard had introduced, called the Heegard decomposition of the 3 manifold. Okay? Now, in fact, life is really simpler. We can concentrate all our activity on this surface. So if you want to describe a solid handle body, the first thing you have to do is give its boundary. Give the surface of genus G, 2 in my picture. And then you have to say which circles on the boundary fill into disks in the interior of the solid handle body. Well, there'll be G of those circles. So a solid handle body can be described by giving the surface of genus G and then G particular curves all embedded in disjoint on the boundary, and I've written down a couple of properties that they have to have. You make the solid handle body by attaching disks to those circles and then filling in the rest with a 3-ball. So I've tried to indicate here the standard solid handle body as it's embedded in 3 space. There's a surface of genus 3. There are 3 curves on it. If you fill those curves in with disks and then fill the rest in with a 3-ball, you'll get the solid handle body, which is represented by the interior of that surface in 3 space. Of course, there are many choices for these curves, but that's how you can represent a solid handle body. You have a surface and genus G, and on it a collection, a family of G embedded simple closed curves on the surface. Okay. But now we have 2 handle bodies. Our 3-manifold is described by one surface bounding 2 different handle bodies. So our surface is described by 2 families of curves, G curves, on this surface. And each one is equivalent, that is by a homeomorphism of the surface, to a standard family. But the problem is how they meet each other, how they're related to each other. So I just said that. So I've drawn you a picture to indicate, this is in fact a picture out of Poincaré's article. This is the counterexample. So this is a handle body, or rather this is a picture of 2 handle bodies. So this is a picture of a 3-dimensional manifold. 3-dimensional manifolds are now pictured or represented by 2 families of curves. So here I have 2 red curves. Colors maybe don't show up so well here. The red curve here and the red curve here, which are completely standard. So they're describing the handle body that's the solid thing you see here. That's maybe the part of the manifold below this surface. Then I have the part of the manifold above the surface, which is a solid handle body with the same boundary. So it will be represented by 2 embedded closed curves on this surface. And here they are. There's this one that winds around this way, and then the other one in a slightly different color. Okay. Now you have to check that there is a homeomorphism of this surface to itself that carries those other 2 rather exotic-looking curves back to completely standard-looking curves. But indeed there is. It's not too hard to show. So this is a picture of a 3-manifold. What 3-manifold is it? How do you calculate its homology? How do you calculate its fundamental group? Well, Poincaré knew how to do all of those, and he describes it. The way you calculate the homology is you take the determinant of a matrix. And the matrix is the matrix of intersection numbers of the red curves with these other exotic curves. So we have 2 red curves, C1 and C2, and we have 2 exotic curves that I've labeled K1 and K2. Let's see how many times K1 meets C1. And this has to be a signed intersection. So I forget which way. I guess this is -1, +1, +1, +1, +1. So I have 4 +1s, 1 -1. That intersection number is 3. Let's see how K1 meets C2. 1, 2, both with the same sign, +2. C1 meets K2. There's C1, K2 meets it twice, both in the same direction, -2, and the last intersection number turns out to be -1. So that's a 2-by-2 matrix. You calculate its determinant. You see the determinant is +1. That means that the first homology of this 3-manifold that you're making by gluing together 2 solid handle bodies is trivial. If the determinant were 0, the first Betti number would either be 1 or 2. If the matrix is identically 0, the first Betti number is 2. If the matrix is not identically 0, but its determinant is 0, the first Betti number is 1. If the determinant is non-zero, the first Betti number is 0, and the torsion coefficient, the order of the torsion group, is the absolute value of the determinant. So this manifold has trivial homology because the determinant of this matrix is 1. Okay. What about its fundamental group? Well, the fundamental group is computed in exactly the same way once you remember that the fundamental group, when you're computing the fundamental group, you're doing something non-abelian rather than abelian. So you don't get to just cancel things. You have to be careful of the order. So you do the same sort of computation. For example, here you get a word in the group which involves generator. As it crosses C1, you have a generator. As it crosses C1 again, you get that generator. Again, you get that generator. Again, you get that generator. But then over here, it crosses C2, so you put in the other generator and then back to C1. So anyway, if you do that computation with this picture, I won't do it out for you, you get the two relations. So you have the free group on two generators, A and B, somehow represented by the cycles, dual to the cycles C1 and C2. And if you just follow those curves around and ask what elements you get these two elements, and they bound handles up above, so they're set equal to 1. So that's the group in question. And if you notice, if you abelianize, you'll get 3a plus 2b is trivial, and minus b minus 2a is trivial. Those are the relations we had before in our abelian computation. Anyway, this is the fundamental group, or the Poincaré group of this example. And what Poincaré said, so the question is, this is the fundamental group. Is it trivial or not? It's not so easy to say offhand. You abelianize it, you get a trivial group. So what Poincaré said was add this relation, and then it's an easy computation to see that the group with these three relators is the same as the group on A and generated by A and B with these three relators. A to the fifth is 1, B cubed is 1, and this A inverse B squared is 1. And that, as Michael said, is the icosahedral group. It's a group of order 60. It's non-trivial, so I've taken this group and added a relation to it and got a non-trivial group. So this group is certainly a fortiori non-trivial. In fact, it's the binary form of the icosahedral group. It's a group of order 120 with a center C mod 2. So that's how Poincaré produced his example and showed it was not the three-sphere by computing its fundamental group, or the group de Poincaré, which he had introduced earlier. This manifold was much studied, it's very important, and has another very beautiful description. It's the space of regular dodecahedra or regular icosahedra in three space. I'm afraid my drawing ability isn't so great, but let's imagine a dodecahedron, a regular dodecahedron. So its faces are pentagonal, and it's regular. As I say, my drawing is not too good. One, two, three, four. Sorry about this. Anyway, you go around, here's a central pentagon. Around it you put 6 more. It makes a slightly spherical looking shape with a ragged edge, and you can glue another one on the bottom. You get a regular a figure with pentagonal faces, 12 pentagonal faces. I've actually seen desk weights, paper weights made out of them with calendars on them. Since there are 12 faces, there's a month on each face. The faces are pentagonal. So this is a regular one of the Platonic solids. If you look at its symmetries, so it's got, let's just think about the symmetries of this regular solid. It's got 12 faces, each being a pentagon. By a symmetry, you can move, because it's regular, you can move any face to any other. And once you've decided where you're going to send the top face, you can also rotate through 5 possibilities. So you have 12 times 5, or 60 symmetries of this regular dodecahedron. So that's the group I've called gamma 60 here. It's the group of 60 symmetries of the dodecahedron. So I look, the space of regular dodecahedra centered at the origin in a volume 1, well, you can get any one of those from a standard one by a rotation. But the trouble is, if you rotate by one of these symmetries, as elements in gamma 60, you get back to where you started, or presented differently, ambiguity in the sense that Etienne was using it last night. So the space of regular dodecahedra is, in fact, the rotation group in three space divided out by this group of symmetries. So I've called it the space of regular dodecahedra of volume 1 and center of mass at the origin in 3 space. So it's a beautiful geometric manifold. Another way to think about it, the SO3, the rotation group in dimension 3, is doubly covered by the 3-sphere. So this is a quotient of the standard 3-sphere by a group of order 120. It's a group that covers the symmetries of the dodecahedron. So that was Poincaré's example. And one point I want to make about this example, I guess I want to make 2 points about this example. It shows why the problem of classifying 3 manifolds is hard. It also shows why it's tantalizing to try to approach it directly without using vast theories, without using all the power of geometry. You're talking about families of curves on a surface. This is something you can see. Now, and as I've shown you, you can calculate the fundamental group from the pictures of the curves. And the question actually, as Poincaré says, becomes, given 2 families of curves like this, so that when you compute the fundamental group, the result is trivial, by a set of elementary moves, which is fairly easy to describe, can you turn this picture into the standard picture? So the picture that will make the 3-sphere, I'll draw it in genus 2, is this one. So the standard picture that makes the 3-sphere, well, we have this is one family of curves, and this is the other family of curves. If you glue 2 handle bodies together using the yellow curves to make one handle body and the red curves to make the other, you're producing a standard decomposition of the 3-sphere. So given some collection of curves like this that computes the trivial group, this computation gives the trivial group when you calculate the fundamental group, can you, by elementary moves, turn it into this picture? Now, actually, Poincaré, when he formulated the problem, first formulated it is any simply connected manifold equivalent to 3-manifold equivalent to the 3-sphere. He went on to say, in other words, can you do this? Of course, it wasn't until 60 years later that it was understood that those 2 questions were the same. If you could manipulate your diagram to get this picture, then you definitely have shown your manifold as the sphere, but it's not clear that you have to be able to do this to show the manifold as the sphere. There might be exotic ways to make a Hagar decomposition of the sphere, but in the 60s, Waldhausen, I guess, proved that, in fact, there was not, and these 2 questions are completely equivalent, something that Poincaré was implicitly assuming. Another interesting twist, it was proven, again, in the 60s, I believe, that for genus 2, you can always do this. Genus 2 is simple enough that one could resolve the Poincaré conjecture, make this transition anytime the group was simply connected into the standard form. But it was not understood how to do it, and still today is not understood how to do it in higher genus. But this is the tantalizing, this is the approach that Poincaré suggested. It's tantalizingly visual, and it's purely topological. And for 100 years, people tried this and various closely related cousins of this, and were not able to succeed. And still today, we have no direct topological argument for this. Okay. So after he said all of this, he ends his, 70-page article by saying, "Mais cette question nous entraînerait trop loin." And indeed, It did. It took us through a tortuous path of 100 years, through topology, some of which I want to talk about now, and eventually into geometry and analysis, which clearly Poincaré was trying to get away from in this article. But in fact, even in his own terms, he cheated. As he was studying curves on a surface, he needed to know if you give, today we would say, if you give an element in the fundamental group, you give a word, how do you know whether or not that word is represented by a simple closed curve or a curve that has to intersect itself? Or suppose you're given two words and you want to know whether or not there's a representative of those by curves that are disjoint. Rather than answering those questions purely topologically, which in fact we know how to do now, he appealed to hyperbolic geometry. So in setting up his purely topological approach to the Poincaré conjecture, he did appeal to geometry to understand the basics about the curves on the surfaces that he needed as input to formulate this purely topological question. So one of the great ironies of this whole story is that what he was doing secretly when he didn't want to tell you, that is some hyperbolic geometry or geometry, is in dimension 2 in order to set up his approach in dimension 3, is exactly the same sort of method that resolved the problem in dimension 3. Well, this is 100 years of topological failure, if you will. People attack this problem over and over again, different variants, and basically they always made the same kind of mistake. And in fact, in the 60s, one of the leading topologists wrote an article entitled, John Stallings, How Not to Prove the Poincaré Conjecture. And he starts off by saying, well, I thought I'd proved the Poincaré conjecture, but that was in another country, and it was a long time ago, so nobody noticed. But to help future workers, I'm going to point out all the standard mistakes that have been made and I have made, so you won't make them. Of course, people continue to make them anyway. Another tantalizing approach to the Poincaré conjecture, again coming from this presentation in terms of simple closed curves on a surface, there's a purely group theoretic question about homomorphisms between certain kinds of groups, and that group theoretic question is equivalent to the Poincaré conjecture. You show it to a group theorist, they say, oh, I don't know, but I bet I can solve that question, and indeed they couldn't. So there's something tantalizingly direct about the question, but it seems to be beyond the direct methods. Okay. Well, what progress did topology make when attacking this question? And here I want to put up a little diagram. This is in the spirit of Atiya's talk. It's a very superficial diagram, but let's think of this as topology. This direction is dimension, and down here we have 0, 1, and 2. Those were all completely understood, so we don't need to worry about them. Here's 3. That's where things begin to get interesting. And then 4, 5, and then so on. And at this direction, we'll do complexity of the manifolds. I won't try to specify what that is. I might say a little bit about it in dimension 3. So my intuition about Poincaré's approach to topology was, okay, we completely understand all of this. We want to understand more what happens in higher dimensions. So let's start here. This is the simplest. This is the simplest three-dimensional manifold, the sphere. This is the lowest dimension where we don't understand anything. Clearly, it's just going to get more and more complicated as either the manifold gets more complicated or the dimension goes up. So we'll start here. But of course, in the end, we want to understand everything. This is just the first step. Of course, in some sense, it's turned out to be almost the last step. So Poincaré got it wrong in both directions. In 1961, Smale did the analog of the Poincaré conjecture, called the generalized Poincaré conjecture, in dimensions 5 and higher. So Poincaré's question about characterizing the sphere in terms of its fundamental group and its homology, well, it turned out to be easier in the higher dimensions than in dimension 3. And Smale did all of them at once. I guess maybe he first did 7 and higher, and then he moved down to 6 and 5. But that left these 2 dimensions. So the higher dimensions are simpler than the low dimensions. And let me just try to indicate briefly why that is. And Michael's already said it. It's because in dimension 3, there's knotting phenomena. So you can have embedded circles in 3-dimensional space or in 3-dimensional manifolds that contract to a point, so they can be continuously deformed to a point. They represent the trivial element in the fundamental group, and they're embedded, but they don't bound an embedded disk. If every time you ran into one of those circles, you could find an embedded disk, then you could solve the Poincaré conjecture and do a lot more. In fact, because of knotting, we know indeed that's not true. The analog in higher dimensions, to prove the Poincaré conjecture in higher dimensions, Smale, again using Morse functions, the same cutting process we've talked about, realized that, in fact, it's exactly the same problem. It's a problem about circles bounding embedded disks. But now you have lots of room. In dimension 5 and higher, anytime you have an embedded circle, just by general, which contracts homotopically, just by general position, you can put in a disk. And that was enough to solve the Poincaré conjecture in these higher dimensions. Doesn't quite work in dimension 4 because the disk is 2-dimensional, so it might meet itself. It was very difficult, and of course it doesn't work at all in dimension 3. It's not true because of knotting. So the higher dimensions turn out to be easier to understand by these direct topological methods that Poincaré had in mind than the low dimensions 3 and 4. It's also the case, as we learned in the 60s, that the more complicated 3 manifolds are easier to understand than the smaller, what seem to be simpler 3 manifolds. And they're analogs of the Poincaré conjecture for those manifolds, which were established by Haken and then Waldhausen. Okay. To understand these more complicated manifolds, one relied on the work in the 50s of Papakyriakopoulos. So he in fact established results that Poincaré and then later Max Dane were implicitly assuming in the early part of the century. It's again related to circles that are homotopically trivial, contract to points, and whether or not they bound disks. So what Papa proved is that if you have a compact manifold, you have a manifold with boundary, and you have a circle on the boundary, which contracts inside to a point in the 3 manifold, then you can find an embedded disk that bounds that circle. It's called Dane's lemma, even though Papa proved it. And then using that, one could cut apart these more complicated manifolds, find interesting surfaces in them, cut them apart, and completely understand them. So in the complexity direction, at least for 3 manifolds, Poincaré was wrong. So these are understood, and the analog of what he conjectured for the 3-sphere is true, and this understanding, these theorems, were purely topological. In higher dimensions, we have these purely topological techniques. Dimension 4 is an interesting story, and Michael put up a picture of Mike Friedman. He was able to take Smale's argument from the high dimensions and push it down in dimension 4 to find embedded disks that these circles bounded. But those embedded disks were incredibly crinkled. They couldn't be smoothed out. They couldn't possibly be smooth disks. That was a consequence of Donaldson's work on smooth 4 manifolds. But Friedman then proved this conjecture. So we had the Poincaré conjecture and its analog in all dimensions except 3, and we had the more complicated 3 manifolds, and we were left with what was originally the beacon, the sample problem, the first test case to try to study, being, in many senses, the last case. And as I've said, topology does not, the pure topological arguments do not seem powerful enough to do this. Well, I've now set the stage for the rest of the talks. I think they will all be, in one form or another, much more geometric than this purely topological introduction I've given you. I've tried to explain to you why topology failed to solve this problem, why people continued for 100 years to try to solve it in purely topological terms, why it's so tantalizing, and I've tried to indicate a little bit of what did come out of studying this problem, which is a history of topology through the 50s, 60s, and 70s until geometry began to come into the picture in the late 70s, early 80s with Thurston's work, and then Donaldson's work in dimension 4, and then finally the coup de grace for this problem with Perlman's work within the last 5 years. Thank you.